All right, I guess we can start. Hi, everyone. Welcome to Math 290. The goal of this course, as I'm sure you all know by now, is to give an introduction to birational geometry of algebraic varieties, focusing on the minimal model program. So let's start with some administrative stuff. So the class time, it doesn't have to be set in stone, so I wanted to propose moving it back 1 hour to 11 to 12:15 Eastern time, in hopes that this will be a little more convenient for people. If a lot of people have a problem with this move, just let me know, and depending on people's preferences, we can not move. We have a week to decide. The second class is a week from today, so it's no problem. Um, Office hours, I'll schedule some eventually, but I haven't decided yet. And then for class discussion, I made this Discord server that I think a lot of people are already on. And I sent the link in the chat right now, and it's also on the website. So feel free to use that to talk amongst each other during the lecture and also whenever. I'll try to monitor that a little bit, but I won't be that good at it while lecturing. I'll post the videos after each lecture at some point. I still haven't ironed out all the details, but I'll put them all in one place and make them available to everyone. So. Anything else? Okay, so if you're officially registered in the class and you need a grade, I think this is the case for a few people. So I will give out some problem sets. And they'll be due 2 weeks after being assigned. And then also for people that need a grade, there'll be some sort of final project. Otherwise, you get to just be here for fun and learn some birational geometry. But if you are interested in doing the problems and want to get some feedback, just let me know. Okay, so I think that's it for administrative stuff. Are there any questions? Okay, cool. Yeah, so feel free, if you have any questions, feel free to unmute yourselves and ask at any time. Okay, so let's start with the actual math. So the overall goal, let's say, of maybe all of algebraic geometry, that's a little facetious, but close enough. We want to classify algebraic varieties. And we can try to classify them up to isomorphism, but that's absolutely too hard. So instead, we can try to settle for up to birational equivalence. So that's our guiding principle for what we're going to study in this class. So just to recall, a birational equivalence or a birational map is some rational map x to y. So rational meaning it's only defined on some open subset between varieties where there exists a u and a v that are open and dense, on which this is a morphism, but it's not just a morphism, it's also an isomorphism. And of course, if we have such an f, we also have its inverse, which is some rational map, and so this gives us an equivalence relation on varieties. Okay, so our overall goal is to classify algebraic varieties up to this equivalence relation. And for everything in this class, we're going to be working over the complex numbers. As many people know, things get a lot harder in positive characteristic, and I won't say anything about that in this class. Okay, so let's start with some background and basic tools just to get us all on the same page. So the first natural question, once you've asked this classification, is how do you produce birational maps? So let's recall our two main tools for producing birational maps. We have blowups. So if Z in X is some closed subvariety, let's say a proper closed subvariety, so not equal to X, then we can define the blowup as this proj of this graded ring where IZ is the ideal of Z. And this proj is relative to X. Okay, and then the important property of a blowup is that it sits in a diagram like this. Where the map down to X is projective and birational. But in particular, it's also a morphism. And this E that lies over Z we'll call the exceptional divisor. And maybe we'll denote it exceptional of pi, where pi is this blowup map. Okay, so those are the first source of birational maps. The second source of birational maps are linear series. So let's just recall and set some notation about linear series. So let's say L is a line bundle. On X. And we pick some non-empty subset of its global sections. Then we'll denote by phi sub v the following map from X to the projectivization of this vector space. There's kind of two ways that you can define this depending on your preference. So maybe the more functorial way is that a point X maps to the class Vx, where V is the subset, the subspace S in our space of sections, such that S of X equals 0. Okay, and so that's one kind of invariant way to define this linear series, where we think of this projective space as a space of hyperplanes in V, and it's only a rational map because there might be points where this V is not actually, this Vx is not actually a hyperplane. But you can also use coordinates. So let's say we pick a basis S0 through Sn, and then we can think of this as X goes to the projective coordinates S0 of X through Sn of X. Okay. So that was mostly to set this notation for this phi. And if D is a Cartier divisor, we'll use the same notation. Phi sub D with these lines to denote the complete linear series for the full space of global sections. Okay, and then some terminology. So given a linear series, we have its base locus, which roughly is a set of points x and x where phi is undefined, but we can give it more precisely as the intersection over all sections of the divisor given by the vanishing of that section. So these are exactly the points where these homogeneous coordinates don't make sense because they're all identically vanish. So that's where phi is not defined. Okay. And of course, the caveat, this complete linear series only makes sense if D is effective, i.e. if this is not empty. Okay, and then a few properties, or just a few definitions of divisors that I'll recall. So we'll say that D is ample if the linear series of some large multiple is a closed embedding. For M large enough. We'll say that it's base point free if its linear series is a morphism, i.e. if the base locus is empty. And we'll say that D is semi-ample if phi MD is a morphism for large enough M, i.e. if MD is base point free, which will abbreviate BPF. Okay, so those are just some definitions. Any questions up to here? Okay, so now some more tools. So again, we want to classify varieties. There are two tools we can use right at the beginning to shrink the class of varieties that we have to work with in the beginning. So the first one is Chow's lemma. Which basically says any variety is birational to a projective one. So for this classification problem, we might as well only work with projective varieties. And this is not too hard, but I won't cover the proof. And then a much harder theorem is resolution of singularities, or Hironaka's theorem. For now, I'll just state a very weak form, and later in the class we'll need a stronger form. But the weak form says if X is any variety, then there exists a proper birational morphism from X prime to X, where X prime is non-singular. Okay, so that we're going to take completely as a black box. So now we can phrase our new goal, which is classify smooth projective varieties up to birational equivalence, which is equivalent to our old goal by these two theorems, or by this lemma in this theorem. Okay, and now that we're in this smooth case, we have one more tool available to us, which is the canonical divisor. So let me refresh some properties of the canonical divisor. So if X is smooth, well, what smoothness gets us is that we have this locally free sheaf of Kähler differentials. And its rank is the dimension. Roughly, we can think of this as we can do calculus locally on X. And from this, we can produce a line bundle, the canonical line bundle, which is this top wedge power of omega. And now we can define the canonical divisor, or a canonical divisor. To be any divisor whose associated line bundle is omega. So this is an extra divisor that we have access to on a smooth variety that we don't necessarily have access to in general. Though later in the course we'll be forced to talk about singular varieties, and then we'll talk about canonical divisors of singular varieties. But for now, we just need this. So the basic example, which will become important, is projective space. So the canonical sheaf of projective space is this line bundle OPN twisted by minus n minus 1. In particular, note here that minus a canonical divisor for projective space is ample, because then we have a positive twist. And this condition will be really important. We're going to call a variety Fano if this condition is satisfied, if minus its canonical is ample. And we'll get to that. We'll get back to that soon. So basically what I want to do for the rest of this lecture then is just to give an overview of the minimal model program. Which is which is a program for carrying out this classification question, but also this word kind of has double meaning because a minimal model program is also something that you can do to a variety, which we'll see as we're discussing it. Okay, so let's start with some prehistory, which is the dimension 1 case, or what we'll call curves. So the first really important fact about curves that you learn is that every curve is birational to a unique smooth projective one. So for curves, this classification up to birational equivalence is actually the same as classification up to isomorphism if we restrict to the smooth projective case. So that makes things quite a bit easier. So now we can carry out our classification scheme. For curves, and this is what we get. So our curves are indexed by their genus, or are classified by their genus, which is the same as global sections of this canonical divisor. And so again, here we're in the smooth projective case. And this could be 0 It could be 1, or we group greater than or equal to 2 in its own category, and we'll see why in a second. So in this genus 0 case, we have, well, just P1. In this genus 1 case, these are elliptic curves. And in this genus greater than or equal to 2 case, we'll just call them higher genus. And we can ask, what are the properties of this canonical divisor? In this genus 0 case, the canonical divisor is anti-ample, which just means that minus canonical is ample. In this genus 1 case, it's actually trivial. So KC is the 0 divisor. And in this higher genus case, it's actually ample. So already we see here a trichotomy where curves are classified based on the properties of this canonical divisor. And we can write down some of the properties that change depending on which case you're in. So we can ask, what are the automorphisms of C? Well, in this genus 0 case, in this anti-ample case, we get PGL2. In this genus 1 case, where K is trivial, we have an infinite automorphism group that's isomorphic to the curve itself, which happens to be a group, times a finite group. And in this higher genus case, when K is ample, we have a finite group of automorphisms. We can also ask, we can also ask about the sections of the canonical bundle. So we already saw that the genus is the sections of K, and it's 0, 1, or greater than or equal to 2. But we can ask, what are the sections of powers of the canonical bundle? So let me give a definition. The canonical ring. This is for any variety, for any, say, smooth projective variety. Is defined as the ring of sections of powers of the canonical divisor. And this is a ring because if I multiply a power of 2 times the canonical and 3 times the canonical, I'll get a power of 5 times the canonical. So it's a graded ring. And one way to study graded rings is to ask, what are their proj? So now in this classification scheme, we can ask, what's proj of the canonical ring? And in the genus 0 case, it's empty. In the genus 1 case, it's a point. And in the genus at least 2 case, it's the curve itself. If you're interested in some differential geometry or have some differential geometry background, you can also talk about the curvature of these various cases, and we can classify these 3 cases by their curvature being positive, negative, or 0. So in this case, it's positively curved. Here they're flat, and here they're negatively curved. And once we have this classification based on the properties of the canonical divisor, essentially, then within each class, we can ask, well, how many curves are there within each of these classes? And this is essentially the question of moduli spaces parametrizing curves in each of these classes. And in the genus 0 case, well, we just have a single curve, so we just have a point as our moduli space. In the genus 1 case, we have a one-dimensional moduli space, and in the genus greater than or equal to 2 case, then there are infinitely many moduli, one for each genus, and they each are 3G minus 3-dimensional. Okay, and just to not be lying, I'll put some warning here and here because there's some extra caveats to talk about moduli spaces in those 2 cases. But now the point is that we've reduced our classification problem. First, we said find a nice representative, and for curves, there's just a unique smooth projective representative. Then we said, how do you classify the properties of this smooth projective representative in terms of the canonical divisor, because it's about the only piece of data we have to work with that's not the trivial divisor. And so we have this nice classification of the geometry in terms of the canonical divisor. And then once we have that classification, then we can say within each of these classes that are based on the canonical divisor, can you classify all the smooth projective curves in that class? And then that's the question of, can you understand these moduli spaces? So that's the overall the classification strategy in algebraic geometry. So maybe let me make that explicit. So proposed, and of course, every step of this fails in higher dimensions, but we'll call this strategy 0. Or every step becomes a lot harder. 1, find a unique or otherwise good smooth projective representative. Classify the geometry in terms of the canonical divisor. And then construct and study moduli spaces that parameterize all varieties within each class. Sorry, and here I should say I used class in 2 different ways. I really mean within each property of the canonical bundle. Okay, so that's our rough classification strategy that we want to extend to higher dimensions. Any questions here? And I actually forgot one thing about this canonical ring that I'll leave as an exercise, but I wanted to point out. These canonical rings are actually isomorphic whenever x and x prime are birational smooth projective. So if they're both smooth projective and birational, then these canonical rings are isomorphic. So that's one reason, other than the fact that it works in the case of curves, that's another reason to expect that this canonical ring or this canonical divisor is a good starting point for this birational classification. Okay. And yeah, this I'll leave as an exercise. Okay, so let's move on to dimension 2. And so again, this lecture is an overview, and we'll go back and prove some of the statements starting in dimension 2, starting next week. But let me write down everything you could hope for and what ends up being true. Okay, so here we have a problem in step 1. So earlier we talked about these blow-up morphisms, and for surfaces, this tells us that, or for at least dimension 2, there are many smooth projective but birational varieties. Okay, so in higher dimension, there are many smooth projective birational varieties, and you can see this because of blowups. So if we have our surface and we just pick any point, then the blowup at this point is another smooth projective surface that's birational to X. So already step one becomes a little more complicated, but this isn't so bad. We can hope that this is the only thing that goes wrong. And so our strategy is to undo these blowups, which we'll call blowing down. And so what we're going to hope for is the following situation, and we'll prove this next week, which I'll call MMP for surfaces. And this name minimal model program will become apparent very soon. So we start with our surface X, and let's call it X0. And then we can hope that we can construct a sequence of blowup maps. So X0 to X1 to X2 down to something XM, where each of these are blowups at a point. And this final XM has the property that it's not the blowup of any smooth projective surface. And these are called minimal surfaces. And so that's really where the name minimal model in this minimal model program comes up. But okay, so we can hope that for any surface we can construct the sequence of blowdowns, basically undo the one issue with step one, and then we can try to classify what are the possible XMs in terms of the property of the canonical divisor. And it turns out there are two cases. XM could be a ruled surface, which means that it's a projective bundle of a rank 2 vector bundle on this curve. So it's some map where all the fibers are P1s. And actually, as a subcase of this, there's also the case where XM is P2, which is birational to one of these ruled surfaces. So we'll include that in this ruled surface case. Or the other possibility is that the canonical divisor of XM is Nef. And so I have to define Nef. So if X is projective and D is a Cartier divisor, then we call D Nef if for any curve any effective curve C and X, the intersection product D dot C is greater than or equal to 0. And we won't really need any, or whatever intersection theory we'll need in this class, we'll cover later. But for this case, we can define this as the degree of the pullback of the line bundle OX of D to the curve. Okay, so our two cases are we have this ruled surface, or we end up with a surface where XM is Nef, where KXM is Nef. And so now we can try to classify or write down the properties of each of these two cases in terms of the canonical divisor. So here are some facts in the ruled case. Our first fact is that H0 of any multiple of the canonical divisor is actually 0 for any non-zero multiple. So there are no pluricanonical sections. So in particular, the proj of this log canonical ring is empty. So this we can think of as analogous to the genus 0 case for curves. This map is a fibration where the fibers are actually P1, so they are genus 0 curves. And in particular, there have anti-ample canonical. So this is this Fano case that we talked about briefly before, i.e. this map XM to C we'll call a Fano fibration. Some fibration onto a lower dimensional variety where the fibers satisfy this Fano condition that minus the canonical is ample. And then 4, XM is not unique. It's very not unique. Basically, we said that XM is the projectivization of some vector bundle, but any two vector bundles are locally trivial, so any two projectivizations are actually birational. But different vector bundles can give you different ruled surfaces up to isomorphism. So XM is very not unique. Okay, so that's the ruled case. Then we have this other case, which is where the canonical bundle is Nef. So in this case, it turns out the first observation is that XM is unique, or the first important fact. And then the second is a very important theorem, which is that if KXM is Nef, then it's actually semi-ample. And if you recall from before, what that means is that some large multiple actually gives you a morphism to projective space rather than just a rational map. And this morphism, we can take its image and just call it Y. So Y is whatever the image of this morphism is. And part of this theorem, I guess, is that this Y, not only does it exist and not only is it equipped with an actual morphism, but because this is the morphism induced by the canonical divisor, then actually Y is proj of this canonical ring. Okay, and so now we can classify the possibilities in this K-Nef case by classifying the possible Y. And so there's essentially 3 possibilities, which are that Y can be 2-dimensional, 1-dimensional, or a point. And so the fact that this theorem is true kind of motivates the next definition, which is that of the Kodaira dimension. So in the surface case, based on just what we've talked about so far, we can define it as the dimension of this proj. And it turns out this definition makes sense in general, but it's not a good definition because it's dependent on a very hard result, which is that in general, this proj makes sense. I.e. it's dependent on knowing that this ring is finitely generated. And that's a very hard and recent result, so we need a kind of a more intrinsic definition that doesn't require a hard result. So we can also define this as the maximum of the dimension of the image of this linear series running over all d greater than 0. So with the caveat that when I have this linear series in general, when I'm not in the situation of this theorem, for example, phi is just a rational map and not a morphism, but we can still define its image by saying, take an open set where phi is defined, take the image of that open set, take its closure, and give me the dimension of that closure. And so this Kodaira dimension we'll define as the maximum of this of these possible dimensions as you vary over all d, and essentially by definition, this is less than or equal to the dimension of x. But it's also possible that there are no sections for any multiple of the canonical divisor. For example, that was the case in this ruled surface case. So this linear series doesn't actually make sense in that case. So in that case, we'll just set the Kodaira dimension to be 0. Sorry, we'll set it to be minus infinity. I don't know what I just did. There we go. We'll set it to be minus infinity if this doesn't make sense. Okay, and so basically now we're given that we can classify things in terms of the Kodaira dimension. This ruled surface case is this Kodaira dimension minus infinity case where we have no sections. And then by this theorem, each of the other cases are either Kodaira dimension 0, 1, or 2. And so now we can study within each Kodaira dimension what happens. So in Kodaira dimension 2, we'll call this XM the minimal model. We'll call this Y, that's the proj of the canonical ring. We'll call this the canonical model. This proj satisfies the property that the canonical bundle is actually ample on the canonical model. So we said on this minimal model, the canonical bundle is Nef, but on this canonical model, Kx is actually ample. There's one caveat here, which is that this is the first place where we have to see singularities. So X canonical is actually singular, so we'll have to talk about canonical divisors for singular varieties, but it's not too singular. But part of the story is classifying the possible singularities that can appear on X canonical. And I should point out, the nice thing is that up to this point, we were only working with smooth surfaces. So in this diagram up here, each of these steps that are blowups at a point all result in smooth surfaces. XM is smooth. The first place we see singularities possibly coming up is this last step where we go from this XM to, I should have put XM here, where we go from this XM to this Y. And then in the Kodaira dimension 1 case, well, that's the case where this Y is a curve. So then XM to Y is some fibration over a curve, and you can show that this is a genus 1 fibration. So basically this happens, and we'll see this, but it happens anytime you have -2 curves. It's basically an if and only if that the canonical model is singular if and only if there are P1s with self-intersection -2 on your minimal model. Actually, the fact that lets us classify the singularities and see that they're not so bad, because they're all the singularities you obtain when you contract some trees of -2 curves. So yeah, so we'll see that later, I think. Okay, so then in the Kodari dimension 1 case, we have this genus 1 fibration. We'll call these elliptic surfaces. And the feature here, what's special about genus 1? Well, these genus 1 curves are the ones where the canonical bundle is trivial. So in this Kodari dimension 1 case, we end up with a fibration over a curve where the fibers are k-trivial curves in our classification for curves. And you should kind of start to think that this classification is going to end up being inductive in these different cases. And then in Kodari dimension 0, well, here we don't get any information from our map to y because y is just a point. But what we do know is that kxm is trivial. Well, that's a lie. dkxm is trivial for some d large enough. And we can kind of think of this as analogous to the Kodari dimension 1 case where the map xm to a point is still a k-trivial fibration. It's just now a k-trivial fibration over a point rather than over a curve.
Do you mean the space of global sections is trivial or the bundle is?
No, I mean that actually some large enough multiple of the canonical or some divisible enough multiple of the canonical bundle is actually trivial.
As a bundle?
Yeah, yep. It's actually, or as a divisor. And so in fact, the space of global sections is 1 for these multiples. And that's why this y is a point. If the space of global sections was 0 for all multiples, then y would be empty. And that was covered in this ruled surface case. Okay, and actually I should really give a definition of this k-trivial so before using it. So I guess I'll do that right now. So I'll give definitions for each of these possible categories. So we'll say, and now this is in any dimension, x is of general type if its Kodari dimension is equal to its dimension. So this is the case we were in here where we have a minimal model and we have a canonical model. And on the canonical model, k is actually ample. We'll say that x is k-trivial if d times k is linearly equivalent to the 0 divisor for some d. And then we'll say that it's Fano, like we defined before, if minus k is ample. And now if we study these cases, we see that in this classification for surfaces, each of our classes are built up from these general type k-trivial and Fano varieties in different ways. So in this case, we have this ruled surface where it's built up from a curve C with Fano fibers. So as long as we can classify all curves and we can classify all Fano curves, then we can classify these ruled surfaces. And of course here it's not so hard because there are all these projective bundles. So the classification is the same as classifying bundles that give you the same projectivization. And in these other Kodari dimension cases, well, in Kodari dimension 2 case, we're in the general type case, and there we have to classify these general type varieties or their canonical models. In the Kodari dimension 1 case, we're now a fibration over a curve with fibers k-trivial. So again, if we know k-trivial curves and we know curves and we know how to classify vibrations, then we've classified all Kodari dimension 1 cases up to birational equivalence. And then in this Kodari dimension 0 case, we have these k-trivial varieties of dimension 2. So some of the upshot of this classification is that these three types in this definition form the building blocks for building birational equivalence classes of varieties. And this will be one of the guiding strategies in higher dimensions. Can we reduce the birational classification to putting together these three types of varieties by these vibration structures or by a program similar to what we just talked about for surfaces. So now we can summarize everything as a theorem. Any smooth projective surface is birational to one of the following. A minimal surface of general type, a k-trivial fibration over a curve, a k-trivial surface, or a Fano fibration over a curve. And each of these cases correspond to the different Kodaira dimensions. And in these first three cases, there's actually a unique minimal model or a unique minimal surface. We'll only call it a minimal model in the general type case. And in this last case, there are many minimal surfaces. Okay, so that's the theorem that we'll talk about next week a bit. And that's a guiding theorem for trying to guess what will happen in higher dimensions. All right, so let's write down the goal in higher dimensions. So in the generality that I'll write down right now, not everything actually holds, or maybe not everything is known yet, but this is the expected picture. So maybe expectation for MMP. So we start with our smooth projective variety X. That's now 3 or higher dimensions. The first step is what's the analog of these blowdown maps that produce for us a minimal surface. So in higher dimensions, we need to construct some, we need to understand these building blocks for simple birational maps that we can use to blow down X to something minimal. So that's the first goal. And then what we hope to see in the end are two possibilities, just like before. Either this XM has a fibration over some lower dimensional variety Z, which is a Fano fibration where the fibers now are Fano varieties of lower dimension. Or possibly XM is Fano itself. That's the case where Z is a point. And another word for this case is a Mori fiber space. And this is the case when the Kodaira dimension, or this is the expected outcome when the Kodaira dimension is minus infinity, or in the other case, then we might expect to end up with a minimal model XM whose canonical divisor is Neff. And now, just like before, we can then, in this Neff case, hope that we can use the pluricanonical linear series to produce an even simpler representative. And so again, the expectation or the hope is that in the KXM Neff case, there's a morphism coming from a large enough multiple of the canonical divisor onto some Z, where this Z is proj of the canonical ring. And this is really a morphism, not just a rational map on this XM. And where here we have two cases in the intermediate Kodaira dimension case, then we expect this phi to be a K-trivial fibration. Over some Z of strictly smaller dimension. And in the general type case, then we expect that phi, the phi is birational, and the canonical divisor of Z is ample. And in which case we'll call Z the canonical model. Okay, so this is kind of impressionistic view of what you want for MMP in higher dimensions. And let me say a bunch of caveats of what makes this interesting, what makes this hard, and some key features. Actually, let me go back to the diagram. Any questions about the actual diagram that we expect to be true? Okay. Yeah, so let me say a few words. Key features we expect. Or key features we know as well. Some of these we know for sure. So the maps rho, these are determined by the geometry of rational curves. And this we'll see in the cone and the contraction theorem due to Mori. Where he uses rational curves to construct these basic building blocks rho for these birational maps. So these will be the analogs of blowing up a point on a surface. Two, we expect that, or we know that minimal models are not unique. So in this Kodaira dimension, actually in all cases, but even in this Kodara dimension non-negative case, where they were unique for surfaces, they're no longer unique. But again, in this non-negative Kodara dimension case, Z, this canonical model, is unique. In particular, implicit in all of this, in this diagram, also is the fact that this R is finally generated. So it's a very hard theorem. In the general type case, so that is equivalent to saying that this Z is birational to X rather than lower dimensional. Then from this point, we can hope to construct moduli. And this, at this point, due to a lot of recent advances, we do have this. So we want moduli of finite type indexed by the possible numerical invariance of C. So I'll hopefully say a few words about that at the end of the semester. And in the Kodara dimension negative case, well, if this picture is true, then in this case, we should end up with this Fano fibration, and it's known that Fano varieties are covered and so we expect that, so we expect this case to be the uniruled case. So this Kodara dimension negative infinity case. So because in the end, we expect to get this fibration where the fibers are covered by rational curves, so everything will be covered by rational curves. Okay, so that's kind of the expectation for the minimal model program. And let me end with a few kind of issues, difficulties, open questions. So the first major issue in carrying this out in higher dimensions, or maybe the 0th major issue, is singularities. So in the case of surfaces, the only place we see something singular is at the very end when we take the canonical model. But in this higher dimensional case, each one of these xi straight from the beginning can be singular. And so in particular, to even make sense of this diagram, we have to generalize the whole story for singular varieties, and we have to know, for example, that these rho actually make sense for singular varieties, not just for smooth varieties. So we'll need to do some detailed analysis of singularities just to even have any hope of carrying out a program like this. The next one, which is related to the fact that you get singularities, are existence and termination of flips. So later we'll define exactly what a flip is. But basically, due to the fact that you get these sometimes very nasty singularities where you can't continue this program anymore, you need to construct these flip morphisms, which basically fix those singularities and let you keep going in this sequence of rows. And so basically, it's a hard problem. When do these flips exist? And why is it that there's not an infinite sequence of these flips? It's possible that you keep going applying these constructions of these various rows and you never end up with XM. So at this point, existence is known. Termination is not known in the full generality that I wrote down. So termination is still open in that generality. Well, I should have called this 1. 2, this last expectation that in the KX Neff case, we hope that this linear series is semi-ample. This divisor is semi-ample is called, well, is one version of the abundance conjecture. And in this full generality, it's completely open, but various special cases are known. So the version that I'll write down here just for this introduction is that if XM, so let me try it this way, if KXM is Neff, then it's semi-ample. And there are various other forms of this abundance conjecture. When this happens, we'll call KXM a good minimal model. So we actually know in many cases that are very useful for a lot of applications that good minimal models exist, even though we don't know the abundance conjecture in general, and we in fact don't know that you can get them from this general setup that I set up here. You have to do some very special birational contractions to end up with a good minimal model under some conditions. 3, there's a question here of finiteness of minimal models. So we said this XM isn't unique in this non-negative Codire dimension case. Are there only finitely many possibilities for XM that could be the output of this program? Or can you have infinitely many? That's a question. Then to finish the classification, you also need to classify Fano and K-trivial varieties. So even if we knew all of this, we still need to, and this is a whole nother field of, well, each of these questions are a whole different field that we won't really say anything about in this class. And we don't need to classify just Fano and K-trivial varieties, but we also need to classify Fano and K-trivial fibrations. And then because of these singularities that come up, and also because of the inductive nature of this whole procedure, the only hope we have at proving something like this is to use induction on dimensions. And it turns out that to make these types of arguments work, it'll be important to generalize this whole picture and this whole expectation to the log setting, where we don't just have an x, but we have an x and a fixed divisor d. Okay, so I'll stop here because it's time now, but I'll just say, so what's our plan from here? So next week I want to do surfaces. So I want to at least sketch out the proof of the main minimal model theorem for surfaces. And then after that, we'll do this Cohen contraction theorem in the smooth case using Morey's bend and break. And then we'll move on to singularities, and we'll have to generalize this Cohen contraction theorem to varieties with the appropriate singularities that come up in this program. And there we'll need some cohomological methods and vanishing theorems. So we'll cover those. And then after that, it's kind of open-ended, where we can talk about maybe more modern and more recent advancements, and talk about more detail what's known in this picture, what's still open, and how people study these things. Okay, I'll stop there. Are there any questions?